Hello, this is Information Service Engineering, lecture number 5, Basic Machine Learning. In this part of the lecture, we are going to talk about evaluation and generalization problems. So up to now, we've seen the different categories of the machine learning algorithms we have, and here we are going to start with the main challenges we face here with the machine learning algorithm. The very first one is the insufficient quantity of training data, because the basic thing we need in order to start training an algorithm is some data from which the algorithm is going to learn from. And that is quite important to have a sufficient number of this training data so that the algorithm is learns better and in the end has a better outcome or better results. And actually recent studies have shown that even the simplest algorithms, they manage to perform quite well in complex tasks, even comparably well to more complex algorithms when there are sufficient training data. The second challenge we face here is the non-representative training data, because there is no way that the algorithm is able to generalize if the training set or the training data is not representative enough, meaning we don't have data there from all the possible categories the algorithm may face. So if we train an algorithm only with the easy cases, there is no way that it will generalize and perform well in the difficult cases as well. And just to give you another example to understand what do we mean here with non-representative training data. So in 1984 in Chicago, this newspaper wanted to have a poll. So to start their poll, they got the registers from the telephone, so the telephone registers. But as you can imagine, back then in 1948, only the rich people had a phone. So this is already a non-representative sample because they excluded all the other people. This is also called biased sample. So that's very important in machine learning. Then we have the poor quality of data, because in the end, no matter how many data you give to the algorithm, if the data are of a poor quality, meaning if they are noisy, if they are erroneous, the algorithm will never manage to perform well. And then we have the irrelevant features. People sometimes tend to put more and more and more features because they think in this way they will help the algorithm to learn better and then in the end perform better. But sometimes they tend to put more irrelevant features to the task itself. That is the irrelevant feature, when the feature is irrelevant to the task itself. And this problem is usually solved with some feature engineering, which we are going to see later on in this part of the lecture. And last, we have the overfitting the training data. Again, it's something that we are going to focus on in this part of the lecture, and is when we overfit the algorithm based on really specific training data we have, but I'm not going to analyze for the moment. So, we said we need data, and let's see how do we use this data, what is the pipeline here in an algorithm. Let's start with raw data collection, meaning the data that we haven't pre-processed. And we have already said, that the larger and the more diverse the data, the collected data are, the better the algorithm will learn and then perform. So first we need this training dataset, which consists of the input features, the X with a blue color, and a target variable for its feature vector. Then this training dataset is given to the algorithm, and the algorithm then learns based on this training set. So we have the learning phase of the algorithm. And after that learning phase, the algorithm, by given an X element or a test data X, and using the hypothesis H, which has already learned or established before, it can predict the label Y for the test X. And that is the process, more or less. But what I mentioned here is that let's consider for the moment the raw data. But actually, what is a very important step here is the data preprocessing that we do. Because typically, to create suitable training data, the collected raw data that we have will be preprocessed. And by this preprocessed, we mainly mean that we will clean up those data, because we want to remove errors, we want to remove dummy values we might have here, absent data, contradicted data, noisy data, and so on and so forth. So preprocessing the data is a very important process here. And there are some standard cleaning steps which we usually follow. First, we start with parsing. This is the first step, which locates and identifies individual data elements in the raw data we have. Then we continue with the correcting phase, which corrects the parsed individual data components using some sophisticated data algorithms. Then we have the normalization step, where here we apply conversion routines to transform data into standard formats. Then comes the matching phase, where there we are searching and matching records across the data based on predefined rules for several tasks that we might need that. And last is the consolidating, where it merges data into one representation, one common representation. And that was the data pre-processing. But let's see now how we manage to get training data and test data, because for the moment we talk about the whole data set we have. So the easiest way here to obtain training data is to split up the original data set. Let's say that that is our whole original data set. So in order to get training and testing data, we are going to split this original data set. The first set is a training data, which is used to train the algorithm, while the second set is the test data, which is used to evaluate the performance of the already trained algorithm. And here we have with the intense colors the training data, and with the lighter colors the testing data. That is a very common technique of doing it, and a common ratio of splitting is 50-50, meaning that we can split the data into 50% using as training and 50% as testing, but that's not the only one. You can do a 70-30, for example, or other ratios. So the problem, though, that we face here in this approach is that obviously the evaluation that is obtained by this method after the splitting is really related to how the data were splitted, meaning that if we were not lucky enough to have representative samples in the training phase, and we had, let's say, only easy cases, then in the test case, where there we are going to have also the difficult cases, then the algorithm will perform poorly. And another problem here is that we know that the machine learning algorithms, they have many parameters, which those parameters need to be tuned at some point. And following this strategy, we cannot tune the parameters neither in the training set nor in the test set. So what do? There is also another way to approach and gather training and test data, which is called the statistical sampling. And we use this usually to get more accurate measurements. So let's see about this sampling strategy. Here, the collected data should be divided into three sets. First, we have the training data, as we had before, which are used to train the algorithm. Second, we have the validation data, something new. So here the validation data are used to keep track about the performance of the algorithm while it learns and how the parameters are tuned. And last, we have again the test data, which are used to evaluate the performance of the already trained algorithm. And this is again how we split the data. A typical ratio here, if we have a lot of data, might be 50% of data will be used as training, 25 as testing, and 25 as validation data, or another ratio can be 60, 20, 20. But again, the problem that we face here is that still we cannot be sure that we have all the representative cases seen already from the algorithm in the training phase, because again here this is a random splitting. So another option that we have here, or another strategy we can follow, is called cross-validation. So the aim of cross-validation is is to ensure that every example from the original dataset has the same chance to appear in the training and the test set. Not the same time, but to be seen in the training and the test set. A special case of cross-validation is called k-fold cross-validation, where the dataset X here is divided randomly to k equal-sized parts. This can be, for example, 5-fold cross-validation or 10-fold cross-validation, so that is divided into 5 equal-sized folds or buckets, or 10 equal-sized buckets. And then the algorithm works as follows. In every step, we keep one of the k parts out, and we use it as a validation set, and the remaining k minus 1 sets are used to train the algorithm. That happens the first time. The second time, we keep out another of the k parts, and we use the rest in order to train. And this we do it k times, and in the end, we average the results. So in this case, since we have the average in the end of the algorithm managed to see at some point every instance as a training and test case. A specific case now, another specific case of cross-validation now is the leave one out cross-validation. So here, given the dataset X, again, which consists of n instances, only one instance per time is left out as a validation set or validation instance, as it is, and all the rest of the instances are used as training. So the first time we keep out, let's say, the first one, and we use the rest as training. Then we keep out the second one for validation and use the rest as training, and so on and so forth. And in the end, again, we average the results. So let's move now to the feature selection, which is something that I mentioned to you in the beginning. So here the idea is that we want to select attributes or features from the available data that are relevant to determine the projected outcome, meaning that they are relevant to solve the specific problem we want to solve. Because really people sometimes tend to put many features that tend to be irrelevant to the task, and those features, they either don't help at all in solving the task, or the opposite, they might mislead the algorithm and make the algorithm have a poor result. Consider the following example. Let's say that we want to build an algorithm that will detect spam emails. Okay, so we will give as input an X number of emails to the algorithm, and we also want to have our feature vector. An idea of feature vector, meaning the different features we can have here, is like, for example, to have as feature all the possible words we have in the English vocabulary. And then treated them as here, as you see here. So if the email contains one of those words, let's say the word Viagra, then we label it as 1, otherwise as 0. And this we can do it for every possible word. It's a valid approach, we could do it. But then what is the point? Should we? Or we should be more careful and make a more elegant decision of our features? And the answer is yes, of course, because this is going to help more our algorithm to perform better than just putting every possible feature there. Some of the problems or difficulties that we face in such a case is that we might have irrelevant attributes. For example, consider the stop words. Why the stop words will be a feasible or a nice feature, an attribute here? How can they help us to decide if an email is a spam or not? They cannot. We might have missing attributes. We might have missing attribute values. We might have redundant attributes, meaning that attributes that they more or less capture the same information, so there is no point to repeat them. Or we might have attribute values that they are noisy. So we've seen now how we treated the data and how the test phase work for an algorithm. But let's see now how we evaluate the performance of these machine learning algorithms. So for the evaluation of the algorithms, we are going to use the following metrics. First, we account for accuracy, which is the ratio of true positive and true negative related to everything, meaning true positives, false positives, true negatives, and false negatives. Then we account also for recall. You remember recall and precision from our previous lectures, where recall is the ratio of true positives divided to true positives and false negatives. Of course, we also account for precision, so how precise the results that we get, how precise they are. which is the ratio of true positives divided to true positives and false positives. And last we have the F1 score or F measure score, which is the harmonic mean between precision and recall. Those are the standard methods we use. But how to compare actually the performance of the different models or our own models when they use different parameters? For that, we account for the ROC curve, which is the receiver operator characteristics curve, and it looks like the one that you see here in the figure, where in the y-axis we have the true positive rate, which is the ratio of true positives divided to true positives and false negatives, which is recall. And in the x-axis we have the false positive rate, which is the ratio of false positives divided to false positives and true negatives. So this ROC curve plots actually the difference between the true positive rate and false positive rate in different classification thresholds or with different classification thresholds. For example, here is the comparison of the two true positive rate and false positive rate for a specific decision threshold, while here is their comparison for another decision threshold. And the natural thing to think here is that by lowering this classification threshold, the algorithm classifies more items as positives. So we have an increase in both true positive cases and false positive cases. Another nice feature we can use here for the evaluation of the result is the AUC, which is the area under the ROC curve that you see here, which measures actually the entire two-dimensional area under the ROC curve. And we can use this as well. And let us now move and talk a bit about the curse of dimensionality. So, we as human, we can say that we are experts in 1 dimension, 2 dimensions, and 3-dimensional spaces. We might be a bit less experts in the 4-dimensional spaces where time is also involved. But in the higher, we are less and less experts in higher dimensional spaces. Where in the machine learning, though, this is not the case, because since we have so many features, we can have so many features, we are often dealing with much higher dimensional spaces, which for us might have counterintuitive characteristics. And let's see why. For example, if we have the 1-dimensional space with k-bins and we want to categorize in those k-bins the n samples, which means that here we have only one feature, then we have to do it for k times n. In 2-dimensional spaces, or 2 features, that should be k in the power of 2 times n. In 3-dimensional space is k in the power of 3 times n, and so on and so forth. And imagine how much this will grow when we have more and more features or more and more dimensions. So, when the dimensionality increases here, the volume of the space increases so fast that the available data, they become sparse. And sparsity here is problematic, especially for the methods that they require statistical significance, which is something that we account for. And let us now briefly talk a bit about overfitting, which we mentioned also in the beginning. So, overfitting models follow exactly the training data. They are really focusing on the training data and trying to predict perfectly, to adjust perfectly on the training data. Here in the example that we have, you see that with a black curve, we have a regularized model, while with the green curve, we have an overfitted model. And you see how it follows exactly the training data, how curvy it is. So the overfitted models, they are too highly dependent on potential noise, of course, and they lack of generalization, because if you slightly change the data, then the model cannot generalize and won't perform as well as it used to perform before. So those models, it's likely to have higher error rate, of course, in unseen data if you compare them to the regularized models. And the message here is that stop training the model before the algorithm overfits. It's never a good strategy or policy. You might have the perfect results for that moment, but with slightly different data, the algorithm will not perform that well. So, in the next part of this lecture, we are going to talk about basic machine learning algorithms.